Yes, of course. Sure. Oh, good morning. Can everybody hear me? Is the microphone working? My name is Peter Reimann, and I thank the organizers, especially Tasaki, for inviting me, and Abhishek Dhar also for inviting me and giving me the detailed instructions. And I asked him if I should give here a slide presentation or better on the blackboard, and he preferred the blackboard. This is with pleasure that I will use the blackboard. So the information flow will not be like in a workshop talk. It will be somewhat slower. So I will do it all on the blackboard. But the title changed because we had to give a title very early. I could not decide at that time. So I decided finally, when preparing the lectures some weeks ago, I decided the following. So the title will be Some Variations on the theme of typicality. Let's say that is a good here. So it will be about quantum many-body systems, obviously, quantum many-body systems. So let's quantum many-body or macroscopic systems of foremost interest in these lectures. In and out of equilibrium, maybe I'll give a very short overview, in and out of, I guess it is too small for the back rows, is it? Bigger, yes. I think so. And mainly it will be about isolated many-body systems, but also it will cover parts of time-dependent, externally driven many-body systems, but not explicitly systems in contact with some environment. I come back to this later. Maybe I put out these glasses. It's easier. I will mainly talk about dynamical properties, about dynamics, and I will focus mainly on analytical considerations here. So it will be not a review, I thought, or as listening to talks. I prefer not to have a big review about everything. It should be a little bit focused. So this will be not a review about some larger specific subject. It will be selected and coherent approach to some specific aspects of typicality. And my background is statistical physics. I am not a condensed matter theoretician, in fact. So it will be not on some special features of some systems like low temperature physics that will not be in the focus, integrable systems, many-body localization, phase transition, spontaneous symmetry breaking classes, whatever, or special models. I will not focus on some specific special features which you find in some systems in our world. I try to take the approach of the textbook statistical mechanics lectures, where you consider some generic systems like a gas in a box or a fluid or a paramagnet or whatever you treat in your textbook and in your own lectures on statistical physics. That is what I have in the background of my mind in such a lecture. So maybe I better bring this over here. Yeah, the level of the lecture. Can I use this maybe? I asked Abhishek what I should take as level, and he answered There will be many graduate students in the audience for which this is intended, and postdocs and active researchers at the forefront, like Tasaki himself, and other researchers, senior researchers from another field, and that is for everybody. So this is like the quadrature of the circle, what I should do here. So I take maybe tendentially a lower level of difficulty. I will start very easily. I take a rather low level of technicality here. So I hope you can stay asleep a little bit. You arrived late. So it is based, this lecture is based on the shoulders of many people. So these are the secret authors in the background of these lectures. I mentioned them. First of all, this is my personal list here, personal hit list. Tasaki. This was my first paper where I got aware of this field. I remember very well when I was a postdoc returning in Budapest in Hungary. I read the paper by Tasaki. I was fascinated. I thought I would like to do something like this, but I was completely unable to enter. I mean, I could not find an entering point into the field. But that was my first paper in this field. The physical review letter by Hall, 1998. And then a little bit later came a paper by Shelley Goldstein and his co-workers. Maybe I write it down immediately, Goldstein. That's how I got into the field, Lebowitz, Gomulka. So they have the habit of listing alphabetically the names. So it is difficult to say who is really the main author. That was our physical review letters, 96, 05, 04, 03, 2006. And when I read this paper, I immediately understood what it was all about. And I remembered coming back to Hall's paper, and that was the moment when I started field. And practically at the same time, independently, Popescu, Short, Tony Short, Andreas Winter, the Nature Physics paper, number 2, 7 or 5. There's always a quarrel with the editors about the page number. On the paper, there is a different page number than in the internet records. So that these were for my personal turning point papers, but of course in the background of all this stands also, and should be named here, von Neumann. We all realized it only later that he was already doing very similar things at the time. Zeitschrift für Physik, 57, page 30. Only it was a little bit difficult to understand, one has to admit. He was misunderstood for a long time. And also, almost unnoticed, but in fact it was mentioned here, but nevertheless it was not really noticed that Seth Lloyd in his PhD thesis did essentially already the same things. That is now even not quite early, but it also went unnoticed. It was, the paper about it was rejected by Physical Review B, I think. They said, there is no physics here, we reject it. but it more or less it contained practically the same things as these two later papers, and many others, of course, and so on. I cannot make here a complete list. So these are the secret authors in the background of these lectures. I will follow similar ideas, and I will work in a similar spirit as these hallmark papers. But I will also the developments in new directions, and I will present it in my own language. You will hardly recognize from the language and the notation the direct connections, but it is in fact more or less the same thing presented in my own way. So the main source, it's not easy to write down here. The main source, but I can briefly mention it. Much of what I will say is contained here in my own paper together with Jochen Gemmer. This will be published in Physica A in press. This is a special issue of Physica A dedicated to Christian van den Broek, who deceased, for my greatest regret, a few months ago. And this will be a special issue, collect some works of his friends and colleagues. It's in press. I will give you more information later. But now you cannot find it. Otherwise, everybody would look into his computer instead of on the blackboard. So, no much bigger introduction for the moment. Let's simply start. And if you have any questions at any time, please ask your questions. So, everybody knows that high-dimensional or Euclidean spaces have many intriguing properties. For instance, the well-known peculiarities of high-dimensional spheres. Almost the entire volume of a high-dimensional sphere is contained in an exceedingly thin surface layer. Everybody has learned. It's surprising. It's not usual in low dimensions. And you can go on. Now, the whole surface layer, in turn, is contained in a small equatorial belt around this surface. It's again almost the whole volume there. And the same for any great circle. And therefore, the same of every intersection of two great circles, again, contains almost the whole volume, and so on. These are the remarkable features of high-dimensional Euclidean spaces. And essentially, so to say, these things are at the background of what I will do here in the following. It's just a variation of these amazing properties of high-dimensional spaces. So let's start with chapter 1, dynamical. Let me abbreviate like crazy. Dynamical typicality. Dynamical typicality. So that is about the issue imitating the behavior. Bit too much. Stay here. The behavior of an ensemble by single pure states. That's about dynamical typicality. A single pure state is not exactly identical, but imitates very well the behavior of certain ensembles. I will specify. So we focus here on elementary textbook quantum mechanics, non-relativistic. External fields are just given. There is no field theory explicitly included. External forces are given. And I only describe the mechanics by non-relativistic quantum mechanics. So we consider a Hilbert space starting point is modeling some system in the real world in terms of some Hilbert space with some orthonormal basis. Let me know if you don't understand some abbreviations or notations. There would be some orthonormal basis labeled by n goes to 1 to capital N. And now it will be a high-dimensional space because I want to exploit these peculiarities of high-dimensional spaces. And it is just some basis, whatever. And, but for simplicity in this lecture, I consider finite-dimensional spaces. I believe that countable infinite-dimensional spaces would not be a real problem, but to avoid all these little peculiarities, I consider finite but high-dimensional spaces. So, for instance, this could be the eigenvectors of some Hamiltonian. So, well, I don't write it down. So it's not a real lecture for students. It could be the eigenvectors of some Hamiltonian. And then this could be the full Hilbert space which model this situation. But it also could be the so-called energy shell. That would be the subspace spanned by all energy eigenvectors whose eigenvalues are contained in the small energy interval. They would span a subspace which you would call the energy shell, and this could be an energy shell, and these would be spanned by those vectors. These are two main examples, full space or an energy shell. But the theory, what I say, will be valid for whatever high-dimensional space you consider. So as I said, I mainly have in mind, as a statistical physicist, high-dimensional many-body systems. So they are large, but the systems are large but finite, so the spectrum is still discrete. You have a large but finite particle number. So the typical dimension of such a many-body system would be exponentially large in the degrees of freedom. So these are really enormously large numbers, typically. Even an energy shell, if you have a particle number of 10 to the 23, then the typical dimension of a small energy shell would still be 10 to the 23. So these are really large numbers in those systems one has in mind, but still finite. But please, nevertheless note, and also these authors emphasize this repeatedly, in principle it can be any high-dimensional space or subspace. Open systems are not admitted here. If you have a little system in contact, weak or strong, does not matter, with some weaker environmental bath, then you simply consider the supersystem of both together, and you treat this supersystem in this framework. So let's now start. So once you have fixed the spaces, you define random vectors in this space in the following way. I defined random vectors, let's say. Random vectors are introduced in the following way. Phi is some, I tell it immediately, some linear operator R, which acts on this sum with random coefficient Cn times this basis vector. So that would be a random vector phi, and the C are complex complex random numbers, n plus IE by n. So I don't say everything, I don't write down. So AN and BN are mutually independent real random numbers, which are Gaussian. Let's say Gaussian AB A and B are Gaussian, Gauss distributed, mean value 0. Let's denote the averaging procedure by an overbar. The mean value of them is always 0. And the correlations would be the second moment, because the mean is 0, it's equal to the variance, would be 1/2. That is the good choice, 1/2. In other words, these vectors are not at the moment normalized. The norm of these vectors is a random number itself for the moment. And R, oh, I forgot to say what is R. R is simply some linear operator on H. Linear. Some linear operator to be specified later. That is the setup. So it follows. Now you can conclude. It is really elementary. It's elementary considerations. What is the correlation of two C's with identical indices? So you would calculate AN minus IBN, AN plus IBN average, which results in AN square plus, because you have two i's, plus BN square average. The averaging feature is a linear operation. You get two average of two squares. Unfortunately, I have 1/2 here, then this gives 1. That would be the self-autocorrelation, if you wish. And if you have two different indices, you would here m's and here n's, and let's say m is not equal to n, and they are independent. They are identically distributed, independent random variables, all these a's and b's. You always have products of independent pairs, and you get 0. In other words, if you put this together, the MCN average is the Kronecker delta n. So this is the first elementary relation. If n is not equal. And in the same way, I will not now do all these calculations here. If you have 4 of them, if you have a product of 4, Cj star Ca m star Cn, right? If you have, of course, 3 products of 3 are always 0. There is always one guy which has no partner, or it's an odd moment. But the next interesting correlation are 4 of them, and you can do a similar but more long calculation, or you can recall the so-called Isserlis-Wick theorem, and you will find a similar result. You have to sum over the products of all possible pairs, and the only contributions arise if j equals k and m equals n, or j equals n and k equals m. That are the only pairs which give a non-vanishing contribution. You can work it out yourself if you don't believe. This is a consequence of the more general Isserlis-Wick theorem. So that's about the C's for the moment. Note, now let's come to the R. I define an operator called rho for reasons which will become obvious immediately. Rho is defined for the moment as R are adjoint. That's the definition of rho for the moment. So this is obviously a Hermitian operator, and it is positive semi-definite. You can convince yourself. And now let's exclude that R is identically 0. That's a trivial case. Let's exclude it. Then we can always normalize R so that the trace of rho is 1. So let's assume normalize without loss of generality by normalization. Normalization, we can always make it so that the trace of rho, I should capital trace of rho equals 1. This we can always make. So far, this is any linear operator, no loss of generality. So therefore, rho is a density operator. Rho is a well-defined density operator. Just formal. For the moment, this is all formal. For instance, let me say first this thing. You can convince yourself it is an easy calculation. If you take another basis, you start with this basis and you take another basis in this space, this amounts to a unitary transformation from one basis to the other. And you can immediately see that this random ensemble, you get the same random ensemble without the R. This will be invariant under unitary transformations, this construction. The statistical properties of all random vectors will be the same, no matter which basis you take here. That's the first main message. So this O and B can be chosen is arbitrary. For instance, it could be single particle product basis. Or any other basis, but single particle product basis is of course a convenient choice in practice. You can think that would be this basis. Now, if you choose R equals the identity operator divided by square root of n, then R square will be a well-defined density operator with trace 1. And now, if you additionally plus normalization, so I do it more formally later, but for the moment I simply tell it, let's take here practically the identity and then you normalize each phi. So you end up with a distribution of vectors on the unit sphere in the space. And then all these vectors will obviously be equally likely on the unit sphere. They will be uniformly distributed for this special choice R. And for other choices of R, they will be non-uniformly distributed. That is to be expected. Now we consider now any Hermitian operator, which is typically an observable, an operator, let's say it is Hermitian. And now let's calculate B bar, which is defined as the expectation. They are not normalized for the moment, but I call it expectation value nevertheless. The expectation value of this B operator averaged over all phi's. Let's consider this average over all possible phi's according to this construction with this R here. It's not normalized for the moment. So I have to insert two such sums here, two R operators. So finally I get the double sum from the phi's M and N. So let's take the index m for this guy, then you get the Cm star, the Cn from this sum, and here you get the basis vectors R dagger BR, the basis vector n. So that is just introducing this definition of phi and then averaging. The only thing which can be averaged are these random numbers. This is non-random. And here you have this Kronecker delta, so you get single sum. Oh, and they are one. You get R dagger BR over this basis. And this is nothing else than the trace of R dagger BR. And now the trace is cyclic invariant. You can bring the last R in front. So you have the trace R dagger B. But R dagger is called rho. So this is the trace rho B. Let's get a little bit. So that's the result of averaging the expectation value of B, trace rho B. And in the same way, likewise, the calculation is a little bit longer, but likewise, oh, I made a big mistake. Let's come back. I marked it, but I forgot it nevertheless. This is called equation 1. This is called equation 2. This is called delta is 3, 4, 5, 6. That would be 7. So. Now I can refer to the numbers. If I exploit number 4, now I go to the next step, which I don't present you the details, but it's true anyway. I exploit now the 4-product identity, and likewise, you find for the variance sigma b square, which is defined as follows. I take the expectation value of B, I subtract the average expectation value, and I square this animal, and I take the average. That's the variance. The mean deviation from the mean square deviation from the mean. That quantifies how far you are from this mean on the average. And you can, I don't present the calculation. It is longer but similar, and you find this will be the trace of rho B square. That is what you find. The variance. That will be number 8. It's a longer calculation, but it is a nice result, I think. Now, from now on, I focus on the cases that the trace of rho is flow purity. So the trace of rho square is always assumed to be small, for reasons which become obvious immediately. I focus, in case I need it, I focus on cases where the purity, rho, that's the purity, mixed state rho, that should be small. So you see it immediately, right? This is a very good restriction. So I choose now B equals the identity as a first step, choose B equals 1. And then it follows from 6 to 8, from 6 to 8. Yes, I exploit 6, 7, and 8. You can see it probably. So now the mean value, B is the identity. Don't write it. The mean value of this thing is 1. And the mean square deviation from 1 is trace rho square. E is now 1.
Excuse me,
Yes?
0 or square much less than 1.
Yes?
That still
No, that is just an assumption for the time being. I focus on operators R with the property that the corresponding row is of low purity. I just focus on them. Here you see why. If this is a small number, I focus on such cases where trace row is small. Because then I can say here something, I can say this mean square deviation is small. That's the purpose of it. On the average, they are normalized. I constructed in this way the whole thing. They are already normalized on the average, and the deviation from this normalization is small, if you allow me to only consider trace row square is small. That means, it means for the vast majority, if I draw random vectors according to these constructions, it's very high probability I will get one which is almost normalized. There may be exceptions which are far from normal, from a norm 1, but most of them will be close. So symbolically, this thing which I described not just now in words, for this situation I create a symbol. These are almost 1, almost ice. That's, so to say, the conclusion here, the first conclusion of machinery. For most phi's which are randomly generated, the norm is almost 1. Now, if statements like this are almost in many papers which I want to publish, and each time the referee says, what does it mean quantitatively? And each time I have to answer the following. To quantify, now I want to make this more quantitative. So, quantitatively, what does mean this statement more quantitatively? I define the random variable x will be the deviation of this norm from 1. Let's consider this real random variable. It's a random variable because the norm is not 1, it's random. Then with this implies the mean value is obviously 0, and the variance, let's also call it sigma without an index. Sigma would be the variance of this x. This is trace rho square. That is just rewriting these two statements here. And then, as usual, for such a real random variable, you have the following property. The probability that x square is bigger or equal than some factor lambda times sigma square. Probability to find an x around the variable x whose square is bigger than lambda sigma square, smaller than 1 divided by lambda for all positive lambdas. That is the so-called Chebyshev inequality. That is true for any real random variable. If you know its second moment, its variance, well, it has first moment 0 here, then this is true. This does not depend on this specific example. So the proof is as follows, if you forgot the proof, or you didn't see it. They are numbers, of course. They are numbers. Then this would be 12, 13. Most of them I don't actually need. This would be, and so on. So let's prove it. If lambda is smaller or equal than 1, it is trivial. Whatever you do here, the probability cannot be bigger than 1. If lambda is smaller than 1, this is a trivial statement. And if lambda, where's my lambda bigger than 1, it is obvious. Namely, if it would not be true, otherwise, let's make a proof by contradiction, otherwise, let's assume lambda is bigger than 1, and this is not true. Let's assume it. It would mean that if you square all, if you take the average of all squares, then this, you have a fraction, this would not be true, you have a fraction of 1 over lambda of realizations, which have lambda square bigger or equal than lambda sigma square. Lambda would be bigger than 1, smaller than bigger than 1, and this would not be true. So there is a fraction 1 over lambda, which have bigger x square, and the rest, the remaining x's have x square at least of 0. That's the rest. You have a fraction 1 over lambda of guys, and that's the rest, which have a x square at least 0. That would be bigger sigma square, which cannot be true because sigma square equals. So it's a contradiction. So that's the proof this equality, of this inequality. Now, okay, that's the end of the proof. So now I choose just an auxiliary quantity epsilon. That would be the trace of rho square to the power 1/3. It's just an abbreviation. If this is a small number, this is still small. And I choose for lambda the value 1 divided by epsilon. It follows epsilon to the power 3 is clearly trace of rho is sigma square. I think this is sigma b. Or this sigma b. Oh, that is my sigma here, yes, right. Here, sigma is trace of rho square. And then, observing this, you get probability that x square is bigger than epsilon square. That is, lambda is 1 divided by epsilon, and this is epsilon to the power 3. So you have here epsilon square left is smaller than epsilon. With this choice introduced in the Chebyshev inequality, you get this. But this, at the same time, is the probability that absolute x is bigger than epsilon. That's the triviality. If x square is bigger than epsilon square, x is bigger than epsilon. So altogether, you get probability. Remember, x was the norm of phi minus 1 absolute, the probability that this norm deviates by more than epsilon from 1, from unity, smaller than epsilon. That would be 16. That is the quantitative version of this statement. Epsilon is the third root of trace row square. Now the probability that it is bigger deviates by more than epsilon from unity is smaller than epsilon. That's the quantitative statement. How is time? Yeah, as I expected. This is the quantitative statement. Now consider you have two operators from H to H, two such operators. Yes.
Evaluate the product definition.
I did not. Did anybody? Can anybody reformulate me? Yes.
Evaluate in 12.
Yes.
Isn't it all?
Oh, for most.
You are using the basic definition.
Yes.
And you are taking R is under root. Really true that it's.
Oh, it's not one for all. It is. Yeah.
But you are you.
It's only on the average it is one. Not each single realization is one. Only on the average. Very good question. So I realize it is not too simple in the end. So are you satisfied? If you take random numbers which can be either 0 or 2, with probability 1/2, then they are 1 on average. But each time you take it, it is not 1. That's the same thing here. Let's consider now two linear operators on this Hilbert space. They need not required to be Hermitian, any linear operator. And then you can show, or you know, that this defines a scalar product. This is a well-defined scalar product on the space of these operators. The trace of them will be a well-defined scalar product. Therefore, scalar product satisfies the Cauchy-Schwarz inequality. So maybe this scalar product times this scalar product. That is Cauchy-Schwarz inequality applied to this well-defined scalar product on the space of all operators. H. Now choose C1 equals B rho and C2 equals rho B. Both are non-Hermitian, but that is fine. It follows, for this choice, it follows that. Now we introduce this C1 and C2. So C1, you have to conjugate it. C1 adjoint will be rho B. C2 is also rho B. So this is simply rho B square here. Introduce this special choice here to get rho B square. And that absolute square, which is, okay, now I would write this again. I would write that is equal to this, that is smaller than this. So I omit this. I simply introduce here again, C1 is B rho, so you get trace. P1 is PO, then you get rho B, 0, and C2 is rho B. So 0, rho B, right? And now the trace is a cyclic invariant. You put this row here, you get rho square B square. You put this row here, you get B, no. You put this B here, you get rho square B square. Both of them is trace rho square B square. But you have a square here, which is, by the way, nothing else than sigma B square. This thing is my sigma B, if you remember. I square it. And now I can take the square root. I take the definition. So with I exploit number 8. Get sigma square smaller than trace rho square B square. That's just the Cauchy-Schwarz. We'll take it here. So denoting the eigenvalues, the eigenvectors of my operator B, I denote them for the eigenvalues would be called Bn, and the eigenvectors beta n, let's say. Then I get sigma B square is smaller than. Now I evaluate the trace in terms of this basis, n. I evaluate the trace here in terms of this eigenbasis of B. So this produces Bn square times beta n. That's an eigenvector of, sorry. It's an eigenvector of B. So this produces me a B square. Here you have beta n whole square beta n. And that is again smaller than, obviously, the maximal value of Bn. That's not really matter. Maximum. I take out this maximum, and what remains is the trace of rho. Trace rho square. That is essentially the norm of B square. The operator norm of B, the operator norm of an operator is the largest eigenvalue in modulus. So that is simply the operator norm of this operator squared. The largest possible eigenvalue is squared. So in other words, variance is smaller than B operator norm times trace rho square. That would be B. Well, I omit this. You see, this is not invariant if you change B into B plus 1. Figure out yourself why this is so. A miracle. Not invariant, and the B goes to B plus 1. Now, okay, that is all statics. Now let's come to dynamics. Let's consider my random vector, which is still not normalized, as the initial condition of a time evolution. And then this initial vector phi goes under the time evolution into a time propagated vector u p of phi. That's the initial condition at time 0. So I start at time 0 equals 0. And then this initial condition is propagated by this propagator into the state at time t. This can be, if this is a time-independent Hamiltonian, this is simply e to the minus I ht. And if it is a time-dependent Hamiltonian, it's something more complicated. Nevertheless, you can write it as the time propagator of the initial condition. That's what it is. So time-dependent Hamiltonians are still admitted. That means the system is not, it may, but it is not required to equilibrate or to thermalize in the long run. It may, but it need not. Now, I take an observable O, and I go into the Heisenberg picture. What I do is nothing than going from the Schrödinger into the Heisenberg picture. The expectation value of O is still not normalized, but I don't care. The expectation value of O equals the expectation value of the initial state, time propagated observable initial state, where OT is U dagger OU. That's the same thing. Phi is UT, phi of t is UT phi, and here the same. And I pull these two U's in together with O into OT. That's going over from the Schrödinger to the Heisenberg picture. And now choose in my general relations the operator OT as B. And now I cannot walk all this distance from 7 to 9 and 18. You can conclude, imply, you use all these equations over there. For the special choice, B equals OT, you get phi OT phi. It's almost equal, it's very close to the average value. Every single realization is close to the average for most such initial states phi. I assume again trace rho square is small. Then you plug it in all these relations, E equals OT. So this will be close to the averaged value. As before, you can ask what is the quantitative statement? It's almost equality. You can show the following strict statement corresponding to this one. Probability that this deviates from the average by more than epsilon times the operator norm of this observable is smaller than epsilon. This you can show in similar lines as before. That's the quantitative statement corresponding to this not so exact statement. So until now, those phi's have not been normalized. And now I consider the normalized counterpart. I draw a random phi according to equation 1. And then in the next step, I define the normalized counterpart of phi, which is essentially the norm of phi. Phi is scalar phi to the minus 1/2 times phi. That's just phi, vector phi normalized. Now psi is normalized. Now for most, oh, this one, yes. Right, thank you. Now we define normalized vectors That would be 4. That means that would be 3. So the normalized phi gives, of course, new expectation values. This would be the new expectation values at time t for this operator. You can now propagate phi. It is the same as the propagate. Does not matter whether you propagate phi or psi. You have the time propagated psi's. They will be they are equal to time propagated phi evaluated with the operator O divided by the norm square. Just plug it in. And they are very close to 1 for most phi's. They are very close to this average value. So that will be close to this one number, phi OT phi, average, most. Initial conditions phi would be, that's no number. Again, so also the normalized vectors are now close to one and the same real number for most initial conditions. The quantitative counterpart will follow immediately. And then you exploit equation 7 over there and 22 to convince yourself that the expectation, phi OT phi average equals, that is probably equation 7, tells you this. And then you recall what is OT. This is built from the O by means of the propagators UT. O. You again exploit the cyclic invariance. You pull this U in front, and you have U rho, U dagger, which is nothing else than trace rho of T O. No, it's not the final result, where rho of T is defined as UT rho UT dagger. That's the usual quantum mechanic propagation in time of a density operator. So this number here is nothing else than the propagated expectation value of O under this mixed state. So altogether you find, now this I can underline, the expectation value if you randomly draw this normalized psi's now, according to the above description, nothing else than the expectation value of the propagated auxiliary operator O, generated for most. No, it does not. It is equally right for most psi's. That's the normalized initial condition. I have no space left, but I have time left. That is at t equals 0. Rho without an argument is rho of 0. Right. But I guess this is a time independent, this property. I have to erase the blackboard. How does it work? That's we will not need so much. Yeah, that would be the quantitative. Oh, that is not well done. Is it acceptable? Cleanliness. Probability, that is just, you can prove this in the same way I did it for the norm. Quantitative counterpart of this approximation. P2. So, oh, that's a very long animal. The probability for this deviation to be bigger than 2 epsilon, operator norm of O is smaller than 2 epsilon. You get the 2 because you have 2 things to combine, the norm of psi and the deviation of expectation value. You have to combine 2 inequalities. This generates this 2 factor. That would be the quantitative counterpart. So if trace, it comes out like this. Maybe you can improve the inequality. That is, at least it is not wrong. You see, if trace rho square is small enough, this will be smaller than the resolution limit of your observable O. You have an experimental resolution limit. If this is smaller than the resolution limit, you cannot really tell the difference between the true expectation value and this. And then with a very small probability, you will see a deviation which is at least experimentally resolvable. In the predominant majority of all cases, the deviation is not resolvable in an experiment. Well, this I leave out. For the moment, all this is true for a given observable O and for a given time point t. You have a small set of exceptions. But for different time points t, this set of exceptions, of exceptional initial conditions, can be a different set. For a different observable, the set of exceptional initial conditions can be a different set. But you can improve on that. You can, for instance, show that there are whole time intervals in which, for most times in this interval, you have an unresolvable deviation there for your observable. You can improve on this. Apart from that, the main implication of this one over there is that if you draw these random initial states, they evolve in time practically indistinguishably. All of them give the same temporal expectation value as this function of time. This is just a function. For each initial condition psi, with high probability, you see exactly the same temporal dependence, the expectation value. This is called dynamical. So this is called dynamical typicality. This finding that most initial states drawn according to this recipe, I will work out this more detailed later, what this can mean. But if you do this, all of them will practically evolve in time the same way. That's called dynamical typicality. That was discovered by Christian Bartsch, now at the moment in my group, together with Jochen Gemmer. This work is a review letters. 2, 11, 0, 403, 209. That's the phenomenon of dynamical typicality. This means time evolution of all these initial conditions is essentially the same. That's what I can say. But I cannot say, and I will not try to say, how this actually looks as a function of time. That's a different chapter. How does this really evolve in time, quantitatively? That's a much more difficult statement. I will not go into this, how the real-time evolution is. But if you know it, or you consider it as given, then all of them evolve the same way. So without further proof, without further details or proofs, I simply communicate to you, writing this density operator in the form, it's spectral decomposition. This is a self-adjoint Hermitian operator, which has some eigenvalues, which I call Pn, some eigenvectors, which I call n. That's the spectral decomposition of this row matrix. It exists. It is sufficient to consider R operators of the form. It is sufficient to consider R operators of the form square root of rho. It's sufficient to consider such R's. Considering more general R's does not lead to any interesting new things. What does mean square root of rho? That means it's defined as the square root of these eigenvalues, which are non-negative projectors. That's the definition of square root. It is sufficient to focus on such rows, because the more general R can be decomposed according to the so-called polar decomposition into a unitary and a diagonal part, and the unitary part is not interesting, because I told you this construction is invariant under unitary transformations. So it is, by polar decomposition, it is sufficient to consider such R's. All more general R's lead to nothing new of interest. It is sufficient to consider cases which only strictly positive weights for all n. You have no, I do not admit zeros here, because zeros here would produce zero eigenvalues here, and this would simply produce directions with zero weight. You would, if you draw your random vectors with an R operator which has a zero in this direction, you simply never draw a random vector in this direction. You can omit it from the beginning. So you can consider only non-vanishing weights, P. Hence, the inverse of rho is well defined. That is simply, by definition, this is the inverse, n to the minus 1. 31, this would be 30, and you can extrapolate the missing numbers. This is then well defined. The inverse of rho exists in this case. Now, another observation, condition 6. I think that was the condition. Trace rho square is very small. Only under, I mean, this is in here, the trace rho square. This is not small, this is of no use, this inequality. The condition trace rho is small. It's not only, it's also, it's of course sufficient. It's also essentially not only sufficient, but also necessary. trace rho is not small, you can show all these things do not work, with one exception, if trace rho is very close to 1. If 1 minus trace rho square is small, then again it works, but this is trivial. But then it's almost a pure state. But that's not really interesting. Essentially, this is not only sufficient, but also necessary. And 6 is equivalent. Condition 6 is also equivalent to the statement that the maximum of these weights, the maximum of all these eigenvalues here, is also a little p, that must be small. That is equivalent to the requirement trace rho square is small. They are equivalent. Let's look at my time schedule. Now that is probably fine. Now this is important, I think, if I write it out. If H is an energy shell, that means you take the energy eigenvalues of your Hamiltonian in a small energy window, and then you span your subspace called energy shell by all the corresponding eigenvectors, eigenvalues in this little window. This is a large but finite dimensional subspace. If this is an energy shell, then your observable is understood as the projection or the restriction of the, I call this the original physical observable. Your observable in the first place lives in the full Hilbert space of your model. And if you now consider here an energy shell, you must restrict this original observable onto this subspace. So you apply a projection on both sides of the original O, and you get that observable O with which I actually did work here. In general, observable onto the subspace. So in general, this changes, this operation, this going from the full space to the reduced space, changes its eigenvalues and eigenvectors. For a priori, this reduced observable has not very much to do with the original one, with some exceptions of, for instance, the operator norm will be smaller or equal to the original operator norm, but in general, it becomes a different operator of the projection. Please remember, this statement is true for time-dependent Hamiltonians still, also true. If H is time-dependent, is t-dependent, then the support of your original rho operator, and if the support will be the energy, maybe the energy shell, and if rho only is supported on the energy shell, the same applies to R. So you pull random vectors out of this energy shell, and thus of the initial state psi may still be an energy shell, may still be some energy shell, which now belongs to, which is meant with respect to the original initial Hamiltonian. But for the rest, as soon as time goes on, you will leave this energy shell. It's practically unavoidable. So as you evolve this initial operator, thus the evolved states, and also the operator O, all of them now live on the full space. Of the considered model. Always time dependent. Hamiltonians, things work, but with the energy shells you have to be careful.
I think the time evolution of the energy shell is a very difficult.
Right.
What is this? Is this a statement or your hope? Or?
Oh, no, that's what you say. At the initial time point, T0, you can start in the energy shell which belongs, and as soon as time goes on, you leave the energy shell. That's the statement.
Your Hamiltonian is time.
Yes.
We
So
don't
you
know
will
what.
leave the energy. That statement is that you cannot say much. You cannot say much. You can't start in an energy shell, but then you leave it. Yeah, that's the statement. Yeah, of H0. You can start with a well-defined energy, and then for the rest of at later times it does not make sense anymore. That's the statement. So with time-dependent problems, this energy shell business is not of much help. Right, you're right. Analogously, or likewise, for several, yeah, that's exactly, I have exactly 2 lines. So this is for one observable O. But if you have 2 observables, O1 and O2, then each of them satisfies such an estimate. And that means the probability that your expectation value will close to the respective average for both O's is still very small with a very high probability. So to say, the set of the bad psi's can at most be added. And the rest, the complement of the bad sets, this was in Hall's paper, bad sets introduced. You see, the good set is at least the complement of the sum of the bad sets. It is still very large. For several observers, you still remain close for most psi's. In particular, for the powers of your original observables, you can consider O and O square and O cubed, or O square minus the average of O square, the variance. So essentially, the whole probability distribution of the possible measurement outcomes, when you measure the observable O, you get the probability distribution of possible measurement outcomes. That is the mean value of these outcomes. And with the O square, you can calculate the variance. You get all the moments, and not all, but a very large number of moments will be very close to the corresponding moments, this mixed state O. So I mean, this is there can be several observables, but their number must, of course, be very much smaller than the Hilbert space dimension n. As long as the number of observables is much smaller than n, this will be true. And so you can get a very high number of moments or a very high number of possible projections onto the different eigenspaces of your observables. And for all these probabilities, they will be all very close to the average value. So it is not only for the mean value, but for the whole measurement outcome statistics, that your initial condition behaves similarly. That is exactly what I wanted to do. Thank you.
Thank you, Peter. So I think we have like 5 minutes for questions.
Yes, the same problem as Hal. If your model has an explicitly time-dependent Hamiltonian, then you still can say the initial state has a well-defined energy. So it lives in a certain energy interval. So the initial density is constrained to an energy shell, and therefore also the R operator will be constrained, and therefore also the initial state phi will be constrained to this energy shell. This construction is still, in principle, you can do it. But as soon as you go on in time, you go away from time equals 0, your operator generically leaves this energy shell. And also your evolved states will leave the energy shell. Therefore, this concept of the energy shell is not of much use. Yeah, I can't. But nevertheless, now you have to work in the full space here. And this is meant in the full space, not in the energy shell, this statement.
The Hilbert space energy shell. Already thermal, right?
Sorry?
It's already thermal.
Oh, no. That comes tomorrow. Tomorrow I will construct R's which generate far from equilibrium initial conditions. That will be the main focus tomorrow. I want to generate far from equilibrium initial conditions. And then I normalize them. They are not normalized, but I normalize them. And for them, this is true. Tomorrow I will show you how to construct an ensemble of far from equilibrium initial states by a good choice of R.
Then
It can be initial, but it can be equilibrium. It can be drawn according to some equilibrium distribution or not.
If it's far from equilibrium, then you can actually say something about the time scale for equilibrium.
No, that's what they say. I can only say they all behave very similarly. I cannot say how they behave. That's of course not. I mean, it covers essentially all models. Sorry?
So let's say you have a large number of observables. What exactly goes on? Something of the order of the dimension of.
You see, for every observable, you have a small set, let's call it the bad set, of initial conditions which do not satisfy the inequality. For each observable, you have a little set of exceptional size. And for the next observable, you have another set and another set. And if you have too many of these exceptional sets, at the end, they will be not any more small altogether. If you
Probability less than some order 1 quantity, then
sorry?
it becomes a huge number, basically, this 2. Becomes an order 1 number.
Yeah, if this epsilon becomes of order 1, then you have too many of them. I mean, still the bad sets could in principle overlap, so the growth would be slower than just adding all of them. But I cannot, maybe it will work, but I cannot say something.
Of course, if you allow any observable, you can of course always construct some very
Yes, of
nasty
course.
observable, which catches a very slight.
If you give me a psi, I can give you an observable which does not work.
While drawing the random state, why this specific choice of Gaussian standard?
It is just for convenience. I think, for instance, then it is invariant under unitary basis transformations. But you can use this numerically. And I think if you numerically generate these random vectors, it will not very much matter. But here for the theory, it's convenient. I have seen some mathematical papers where they extend theorems for non-Gaussian. It can be done, but maybe for the main principle, it is not so important. But it is not an a priori strict restriction. You can do other random numbers.
It's exactly the same if you consider a uniform measure on this large dimensional unit.
Yeah.
There's only one uniform measure.
Before you apply your R operator, this is in this Dhar uniformity. They are all distributed. Yeah.
Okay, so thank you very much.
Okay.